So it's always interesting to see what the data is actually about. The higher a person is above Earth, the further they can see. And they drew you a picture here about why that's true. Oh, you're frozen, sorry. Over here they drew you a picture, so the higher you are above the Earth, the farther you can see. The table shows the distance in kilometers a person can see from a height that's 8 meters above the Earth's surface. So these here were the distances, and then they plotted them for you. And so then they asked you which one would be appropriate for modeling the relationship between the variables. So just based on the shape, does it look linear? No. So we know a linear is a straight line, right? So if you didn't know that, or if you just maybe weren't 100% sure about that, draw a picture. Linear. Is it logarithmic? Some people say yes. The shape of a logarithmic graph, it has a vertical asymptote like that. You don't see it ever. It's fine that it's not on there. And then it levels out vertically there, and then it goes like that. Okay? So that looks pretty promising, the logarithmic. Is it exponential? You probably could manipulate an exponential graph onto that one because exponentials and logarithms are inverses of each other, but it would not be such a natural fit because the exponential, it levels out horizontally instead of vertically, okay? So it looks more like that. And then the power function is just a group of functions that have x as a base and different numbers as the exponent. And they could look as simple as like having kind of straight but having like a little wiggle in them like that, or they could look like a quartic function. I mean, technically quadratic and cubic and quartic are all power functions. So power functions can look different from other functions. But right now we're just using our eyes to determine. So we're going to base our answer on the shape of the graph. So here we're going to say the shape of the graph. And would you guys agree that the shape best matches logarithmic? Yeah. All right. In my answer key, whoever made this answer key, they have this like clever way of remembering these shapes. I'm going to show it to you in case you like it. Personally, I found it difficult to try to like manipulate. But if you like it, if it helps you, then you can take it. So I'll zoom in on this. So here, see how clever it is? They made the linear line on the L. For the logarithmic, they made a logarithm on the R. Exponential comes out of the X, and a power. That's one example of a power with a W there, but it's only one example. It can look really different. I'm going to leave that for just a minute in case you're trying to get it. And then I'm going to look in Desmos at these shapes real quick too, just so that you can know, like, this is a resource for you. Obviously, you can use your calculator too. Actually, yeah, no, I just used Desmos because it was quick. But you can graph these in your calculator just as well. Okay. So down here, we're given the steps for nonlinear regression. And it starts the same way as linear regression, putting your data in your lists, and then choosing zoom stat and looking at your scatter plot. Sometimes you have to turn your stat plot on, especially if your memory's been cleared. And these are the basic shapes that we're looking at, but in this lesson, we're going to focus on logarithmic, exponential, and power. But these are all shapes that you might need. So let's just review what some of those might look like. We just talked about linear. Okay, remember quadratic will be a parabola, could open up or it could open down. Oh, it would help if you could see it. Cubic, it can look a couple different ways. One way it can look is just to have like one little turn in it like that, or another way it can look is like that. So a cubic could have up to 2 turns in it. It could have 0 turns or it could have 2 turns. Quartic, same thing. It could have up to 3 turns. So it would be like quartic might be like a W. But also there's like this wider parabola that's also a quartic. So it could have 1 turn or it could have 3 turns. Logarithm could look like the one we just looked at, like this. But it could also be this way, right? Exponential, it could be like exponential growth, or it could be exponential decay. Power can look all kinds of ways, but if there's a slight curve in the data, that's often what we're looking at, a slight curve. And do you guys remember what sinusoidal looks like? Sinusoidal includes what two trig functions? Sine and what else? Cosine. Good. So sinusoidal graphs look like this. And the difference between a sinusoidal graph and, like, for example, a quartic graph is that the quartic graph at the end, it's going to keep going up or keep going down. But the sinusoidal graph is going to keep oscillating. It's not going to eventually go up or go up down. Okay, that's why I don't usually put arrows at the ends of my sinusoidal graph, because the arrow would indicate that then it just keeps going up or down, and it doesn't do that. All right, logarithmic models. On our calculator, they do a natural log. Remember that ln is natural log, which is log base what? Close. That's the other special one. Log base e. Okay? So ln is natural log, which is log base e, and that's the one that they do on your calculator for a logarithmic model. You can look at it and you can see it's clearly not linear. You can create a linear relationship between y and ln x, but you don't have to do that. Your calculator is going to do this for you here. So you're going to enter your data, and we're going to do stat calc linreg, no, not linreg, lnreg, which is different from linreg, which is the linear one. And then we're going to write it in this format, y equals a plus b ln x. So let's look at this first problem, and let's put this data into your calculator. Oh, also, guys, when we're doing the nonlinear ones, we're looking at the coefficient of determination, which is r squared. So when you do these, look at r squared, which is called the coefficient of determination. To determine the fit. It's going to tell you if it fits well or not. So we only use the r for linear, and for everything else we're going to use r squared to tell you the fit. R squared is not the best way, though, to compare models. So, for example, in that first problem, let me just show you real quick. On this first problem here, we could see from the shape that it was logarithmic. But I did the regressions just out of curiosity because I knew that the r squared is not reliable for comparing models. And I got the best r squared for the power model, even though it's clearly logarithmic. So trust your eyes first on the shape of the graph, and then after that you can decide, after you've chosen your function, you can decide how well that regression fits. So let's put this in your calculators. I'll put that in my calculator too. All right, so the first thing we want to do is sketch the graph. If your stat plot's not on, you go to second stat plot to turn it on, and you'll press enter and you'll turn it on over here, but this one's on. Then you can do zoom stat, which is zoom and then 9, and we get this shape. So let's get that shape onto your paper. Okay. All right, we don't have any labels here. We just have X and Y. What shape would you say that is? Yes?
How did you get to the graph?
Oh, let me go back and show you. So the first thing you have to do is make sure your plot's turned on. So go to second and then Y equals. And if this is off up here, then you press enter. And you have to press enter on and go through the whole list. Okay? And then after that, you're going to do zoom and then stat plot. Zoom stat, which is 9. You getting it now? No? Okay. I'll come and take a look.
Oh, never mind. I got it.
Good, okay. All right. So explain why x and y are related by a logarithmic model. What would you say? Obviously, it's the shape of the graph, but how would you describe this graph? Does it have a constant slope like a linear function? It's not going up the same amount each time, right? Does it increase more quickly at the beginning or at the end?
Beginning.
At the beginning, right. So a logarithmic graph increases more quickly at the beginning. So I'm going to write the shape matches a logarithm, and then I'm going to write the other. The y values increase quickly at the beginning. All right, so since it is logarithmic, that's the regression we're going to choose. And at the top of your paper, it tells you like the numbers for each regression. It says logarithm is choice 9 when you go into stat calculate. So you're going to go back into your calculator and do stat calculate. And the 9th one, linreg and lnreg look very similar. Lin is linear and ln is logarithmic. Choose 9. And make sure you have list 1 and list 2. Kaden points out that you can store the regression equation right here. And to do that, you would do it in y1. Kaden, did you find the command for y1?
No, I could not.
Does anybody know where that is, the command for y1? No? No? Okay. I'm going to look it up, or you can look it up. We'll find out where that is. But when you store it, that just means that when you press y equals, it will show up in there. Okay? So we'll figure out where the command is for the y1. But you don't need it at the moment. I'm going to go back to stat and calculate in 9. And I'm just going to enter through the list since I can't find it right now. All right. And it has a value for a and b, and I'm going to need those to 3 sigfigs. So I'm going to write down on my paper, a equals 0.692, and b equals 5.23. And then I'm going to use the structure at the top, a plus b ln x. So it's going to be y equals 0.692 plus, and then 5.23 ln x. Now note that your r squared is 0.992, and it doesn't ask you about that, but we do need to know about this anyway. So r squared is equal to 0.992. Is that close to 1? Yeah, it's really close to 1. So this would be a very strong correlation. All right, sorry about the sideways there. Okay, so you use your a and your b value to build your equation. You need to explain why it's a logarithmic model more than just the shape. You got to write down what about the shape makes it look logarithmic. And we added our own little note here about the r squared. It didn't ask about that, but you do need to know about the coefficient of determination. Thank you. I think it's on your desk.